Okay, now here is an exercise on the utilization of the superposition theorem. And the idea is we want to calculate the current in the rightmost branch, which means that we want to solve for the current through the resistor R5. In order to do that, we use the superposition theorem, which states that the current in any given branch of a multiple source linear circuit can be found by determining the currents in that particular branch produced by each source acting alone, with all other sources replaced by their internal resistances. This means that if we want to calculate the current through R5, we need to replace the 2-volt source with its internal resistance and then solve for the current R5, and then replace the 3-volt source with its internal resistance and then solve again for this new current R5. Then we add those two currents together, which was obtained from two different approaches. That's what superposition theorem states. In this circuit, there is no internal resistance for the voltage sources. This means that we can simply replace each of the voltage source by a short. So let's solve this problem by first replacing the 3-volt source with a short. In other words, we ignore that and then replace that with a short. Okay, this means that in order to solve for the current R5, we need to first simplify this equivalent parallel resistance, and then let's call that R6. And then we need to solve for this equivalent resistance, okay, which we will call R7. And then we solve for this equivalent resistance, which we call R8. And then finally obtain the total resistance, which we now call R9. From there, we can solve for the currents. Let's solve for R6 first. R6 is equal to 1 over 1 kilo ohm plus 1 over 2.2 kilo ohm. And that is given by 0.69 kilo ohms. Okay. Next, we need to solve for R7. R7, this orange box here, is the series resistance of R3 and R6. So R3 plus R6. So that gives us value of 1.69 kilo ohms. Now R8 is the equivalent parallel resistance of R2 and R7. So that's 1 over 1 all over 2.2 kilo ohms plus 1 over 1.69 kilo ohms. This gives us 0.96 kilo ohms. And then R9 is nothing but R1 plus R8. Okay, so that's 1.96 kilo ohms. R9 is the equivalent resistance of the whole network of resistors. This means that the current I1 is equal to 2 volts divided by R9. So that's 2 volts divided by 1.96 kilo ohms. And that's 1.02 milliamperes. Okay, so I1 is the current passing through R1 and the current passing through R8. Now that current passes through this junction and separates to R2 and then to R7. To solve for R2, we need to determine the voltage across R2. The voltage across R2 is V2. But we see that here's the source, here's R1, and this is V2. So that's a voltage divider equation. So that's R8 divided by R1 plus R8 times 2 volts. Replacing these values, R8 is 0.96 kilo ohms divided by R1 plus R8 is 1.96 kilo ohms times 2 volts. So V2 is equal to 0.98 volts, which means that the current through I2 is equal to V2 divided by R2, which is equal to 0.98 volts divided by 2.2 kilo ohms, or I2 is equal to 0.44 milliamperes. So we have 0.4 milliamperes going through here. So we have 1.4 milliamperes going through here and then 0.44 milliamperes going through here. The rest is going to R7. So the current through R7 is 1.04 milliamperes minus 0.44 milliamperes. So that's 0.60 milliamperes. Okay, and that's also the current going through R3 just before it's separated across that junction. So that means that the current through I3 is 0.60 milliamperes. Okay, so what about the current through R4 and the current through R5, which ultimately we want to solve? 0.6 milliamperes passes through R3, and that's separated at this junction here, and it goes through R4 and R5. So in order to solve for the current through R4 and R5, well, we only want to solve the current through R5. We need the voltage across these two junctions here. And to solve for the voltage across these two junctions, we see that it's again a voltage divider equation from R3 to here, okay, where you consider this as the source voltage. We already know what this voltage is. That's the voltage across R2, which is 0.98 volts. So all we need to do to solve for R5 is first to solve for the voltage across this junction. The voltage across that junction, let's call that V5, is equal to the equivalent resistance R6 divided by R3 plus R6. Sorry, multiply that by 0.98 volts, which is the voltage across these two junctions. R6 is 0.69 kilo ohms and R3 is 1 kilo ohm. So this means that V5 is equal to 0.40 volts. So that means that the voltage across these two junctions is 0.40 volts. Now we can solve for I5 because we know that there's 0.4 volts here. So I5 is equal to 0.4 volts divided by 2.2 kilo ohms. This means that we have 0.18 milliamperes. Okay, so that's when we short the 3 volt power source. Now to solve for the current when the 2 volt source is shorted, we see in this case that R1 is parallel to R2, and that's going to be our R6. Then we see that R6 is in series with R3, and that will be our R7. Next, R7 is in parallel with R4. And now we come to a point where we figure out what is the correct circuit here. So if we redraw this, we have our R7 like this. Then we have R4 in series with our source voltage, in series with our source R4, in series with our source voltage are 3 volts, then R5. Okay, how do we redraw this? So first let's draw the 3 volt voltage, source voltage, like so. Then we know that it's connected to R4. like so. And then there's a junction that connects to R5 and R7. Now R5, the other end of R5 is connected to the negative terminal of 3 volt source. And also the other end of R7 is also connected to the negative terminal of 3 volt source. So this is what it looks like. So the next step would be to simplify R5 and R7. This is going to be our R8. Finally, we have our R9, which is just the sum of R4 and R8. Okay, so now that we have that figured out, let's then solve for R9. The first thing we need to solve is R6. So R6 will be equal to 1 over 1 kilo ohm plus 1 over 2.2 kilo ohms. And that will give us 0.69 kilo ohms. Next we solve for R7. R7 is equal to R6 plus R3 because they are in series. Okay, since R3 is 1 kilo ohm, this will be 1.69 kilo ohm. And then R8, as you see from here, is a parallel combination of R5 and R7. So that's R8 equals 1 over 2.2 kilo ohms plus 1 over 1.69 kilo ohms. And that will give us 0.96 kilo ohms. Okay, and then finally R9. Okay, we'll put R9 here. It's just R4 plus R8. Okay, which means that since R4 is 1 kilo ohm, this will be 1.96 kilo ohms. Okay, it's a bit familiar. Okay, and that's because the circuit is actually symmetric. Okay, about this. Okay. Of course, I could have started with that, but it's easier like this, especially if you're applying the superposition theorem first. Okay, so now that we have that, we can now solve for the current going through R4 and R8. So the current going through R4 and R8 is 3 volts divided by R4 plus R8. Let's call that I4. So that I4 is equal to 3 volts divided by R4 plus R8, and 3 volts divided by 1 kilo ohm plus 0.96 kilo ohms. So that I4 is equal to 1.53 milliamperes. So this is the current passing through R4. So that's 1.53 milliamperes, but it's also the same current passing through R8. And that current separates into two currents, I5 and I7 here. Now to solve for I5, which we are really after, we just need to get the voltage across this junction here. And to do that, we recognize that this is another voltage divider. To get V5, let's call that V5, we equate that to R5 divided by R4 plus R5 times 3/4. So V5 is equal to R5 divided by R4 plus R5. R5 is 2.2 kilo ohms. R4 is 1 kilo ohm plus 2.2 kilo ohms times 3 volts. And that will give us 2.06 volts. Okay. So the voltage across this junction is 2.06 volts. And if we divide that by R5, it will give us I5. So V5 divided by R5, 2.06 volts divided by 2.2 kilo ohms, which results to a current of 0.94 milliamperes. And that is if 2 volts was shorted. So according to the superposition principle, the total current through I5 is 0.18 milliamperes plus 0.94 milliamperes, which is equal to 1.12 milliamperes. Okay, so that's how we use the superposition theorem.